This chapter has a lot of information, but we want to concentrate on doing calculations involving decibels and noise. In the figure shown, we show a symbol for amplification. This is not a schematic diagram, simply that we show that we're trying to amplify a signal. In the first figure, we're trying to amplify a signal, and so we put in a signal of 25 milliwatts, and after amplification, we have a power coming out of 3.9 watts. So we want to express this in decibels. We say that the power gain is 10 times the log of power out divided by power in, or 3.9 watts divided by 25 milliwatts, which is 22 decibels. So you see the decibel scale is useful for expressing very small numbers and also very large numbers. Let's do the same thing again. This time we have a power input of 550 milliwatts, and after amplification we have power out of 100 milliwatts. If we do the same thing again, the power gain is 10 times the log of 100 milliwatts divided by 550 milliwatts. This time it equals negative 2.40 decibels. If we have negative amplification, what we have is attenuation. Instead of building up a signal, we lowered it. The previous examples, we had measurements in power, which is not easy to measure. It's usually easier to measure volts. When doing observations in volts, as from an oscilloscope, we would say that the voltage gain is 20 times the log of V out divided by V in. So in this example, let's say we put in 1 volt and we get out 2.5 volts. Then the gain in decibels is 20 times the log of 2.5 volts divided by 1 volt, or 7.96 decibels. When doing practical measurements in decibels, it's always necessary to have a reference for 0 decibels, and different applications have different values for 0 decibels. In the audio industry, often they say, let 0 dB equal 1 milliwatt. In that case, we say 0 dBm equals 1 milliwatt. Let's say we have taken a measurement of a certain amplifier and we find that the output is 200 milliwatts. Now we want to express that in decibels. Since we know we're dealing with dBm, we will say that the power output gain in decibels is 10 times the log of 200 milliwatts divided by 1 milliwatt, and that equals 23 decibels. Why did we use 1 milliwatt? Because we're using a reference of 0 dBm. So we will say that we have a gain of 23 dBm. In the case of more powerful amplifiers, we could say let 0 dBW equal 1 watt. Once again, let's say we measure an output of 5 watts and we want to know the gain in decibels. So again, we would say the power gain is 10 times the log of 5 watts divided by 1 watt. That equals 6.98 decibels, or 6.98 dBW. Let's look at a signal that we've amplified, and we're looking at it on the oscilloscope, and we see our signal, and our signal is a 100 watt signal. But then on top of that, we see some distortion, and this is going to be the noise. And so in this case, let's say we have a noise of 0.1 watt. The signal to noise ratio is calculated by saying it's 10 times the log of the signal in watts divided by the noise in watts. In this example, then it's 10 times the log of 100 watts divided by 0.1 watt. It equals 30 decibels. In this case, the bigger the number is better, because that means that we're amplifying the signal much better than the noise. Absolutely every electronic component produces noise. It produces noise when it amplifies, it produces noise when it receives a signal, a resistor, capacitors, everything produces noise. Let's look once again at our amplifier. In this case, we have an input of 100 microwatts, and with it comes noise of 50 microwatts. And we're going to amplify this, and then at the output, we have an output of 1 watt with output noise of 0.75 watts. Now we want to measure is the noise figure. The noise figure is calculated by saying it's 10 times the log of V in divided by V in noise. The whole thing is divided by V out divided by V out noise. If you look at that formula long enough, it's signal to noise ratio of the input divided by signal to noise ratio of the output. Let's put in our numbers then and say it's 10 times the log of 100 microwatts divided by 50 microwatts, and then the whole thing is divided by 1 watt divided by 0.75 watts. When we get done with all the divisions, we find that we have a noise figure of 1.5 decibels. In this case, the noise figure number should be very low because that indicates that we have controlled the noise when we went through a large stage of amplification. Those of you who started building the radio, you will notice that on several occasions it will ask you to measure the gain of a stage of amplification, such as transistor. In that case, always convert the gain to decibels, like we've learned in this chapter, because that's the best way to deal with amplification is with decibels.